Hello, my name is Jakub Bělín. I am affiliated at the Central European Institute of Technology in Brno, Czech Republic, and today I am going to talk about how to rotate an image using a triad of non-parallel lenses. To warm up, let's start with something simpler. Given a pair of coaxial lenses L1 and L2 of focal lengths f1 and f2, separated from each other by a distance d. Anyone who came along with engineering optics knows well that imaging due to a pair of coaxial lenses can be described by the same equations as imaging due to a single thick lens of focal length f, whose principal planes P and P' intersect the optical axis at the principal points P and P'. Let me recall that principal planes of an imaging system can be defined such that P is imaged to P' with a magnification +1 due to the system. Sometimes, the object being imaged due to the imaging device is said to be in an object space, and the respective image is said to be in an image space. Great, but what if the lenses are not parallel any longer? Maybe you have an experience with building and fine aligning a complicated optical setup, and during the data collection you found out that two of the lenses in the setup are not parallel any longer. What to do in this case? Shall we put all the data already collected into the bin, or is there any clever way how to interpret the imaging due to the pair of non-parallel lenses? I am aware of the fact that real lenses work well only in a paraxial regime, and thus people do not study lens systems in which some lenses are expected to work non-paraxially. However, I would like to show you that such non-paraxial systems of lenses have a so far unappreciated potential to form devices with unusual imaging properties. Okay, so the idea is the following. The pair of non-parallel lenses differs from the parallel one just by the non-zero angle between the lenses. Therefore, there is a hope we'll be able to find a coordinate system in which the mapping between the object and image space, performed by the pair of lenses, is of the same form as a mapping due to a single thick lens. In general, such a coordinate system might be non-orthogonal, and the set of basis vectors in the object space might differ from the corresponding set of basis vectors in the image space. For this reason, we will first check that the imaging equations preserve their form in a simple case of imaging due to a single thin lens, but described in a non-orthogonal coordinate system. This figure shows a case when object O is imaged due to the lens to an image I. Here are the corresponding imaging equations in a Cartesian coordinate system XYZ. Now, let's choose the new coordinate system UVW such that U and V axis span the plane of the lens, and the W axis is chosen to lie in XZ plane such that it makes an angle alpha with that axis. From the figure, one can deduce that Z is equal to W times cosine alpha, and insert this into the imaging equation to obtain this equation here. Here, if we define the guy on the right hand side as an inverse of a so-called projected focal length G, we get an ideal thin lens imaging equation again. Moreover, employing the similar triangles yields that W prime over W equals to U prime over U, which is equal to V prime over V. This little observation encouraged us a lot to find an analogous non-orthogonal coordinate system in which the two skew lens imaging equations are of the same standard form. We will call such coordinates the lens imaging coordinates. To find the lens imaging coordinates, we first define a two-lens optical axis as a line through both principal points of lenses L1 and L2. For this axis, we calculated the projected focal length f and calculated the positions of principal points P and P' using the standard formulas. Then we realized that there is a special line V where the lenses intersect, because any point lying on this line is clearly imaged back to itself due to the two-lens combination, and therefore it is an intersection of the principal planes P and P'. Indeed, we showed that any plane parallel to P is imaged due to the two-lens combination to a plane parallel to P'. Therefore, we call planes parallel to P object-sided transverse planes, and similarly, the planes parallel to P' the image-sided transverse planes. Object-sided transverse planes make an angle theta with x-axis, and similarly, image-sided transverse planes make an angle theta prime with the same axis. Now we will choose the following promising candidate for the lens imaging coordinates. First two basis vector v, w and v prime w prime are chosen to be parallel with line v and with w axis respectively. The remaining basis vectors u and u prime are then expected to lie on an intersection line between the plane M and planes P and P prime respectively. The lengths of vectors u and u prime, however, must be chosen such that the principal planes P and P prime are imaged to each other with magnification +1. To find the desired lengths of u and u prime, we define a Cartesian coordinate system x, y, z as follows. Then the lengths of vectors u and u prime are chosen in this way. With this candidate for lens imaging coordinates in hand, we found the respective coordinate transformation from xyz to uvw and from u prime w, v prime w prime back to x prime y prime z prime. And then we confirmed by a thorough calculation that the image position x prime y prime z prime obtained by this equation here coincides with the image position obtained by successive imaging first due to L1 and then due to L2. Perfect. We showed that imaging with a pair of skew lenses corresponds to an imaging due to a single thick lens, but with an additional shearing caused by the non-zero angle between the lenses. And now we are finally ready to propose a system of lenses whose mapping coincides with a rotation of the object space. Our concept is based on the two skew lens imaging discussed so far, which yields mapping between object and image space that corresponds to the one due to a single lens, but with sheared object and image spaces. However, if another shearing is implemented such that it exactly cancels the original one, the resulting mapping might correspond to the rotation of the object space, and we call such a mapping an image rotation. The additional shearing can be performed if one inserts lens L3 to the two-lens system, which is called D here, such that the plane of L3 coincides with P prime, and the object-sided focal plane of L3 coincides with the image-sided focal plane F prime of the system D. By doing so, all the object-sided transverse planes will be imaged to the image space due to this new system D with a magnification equal to +1. To cancel the coordinate shearing due to D, the principal point P3 is required to be placed to a position such that all lines which are perpendicular to the object-sided transverse planes become perpendicular also in the image space. To find the desired offset of lens L3, it is very convenient to employ the lens imaging coordinates we defined earlier, since in this coordinate system, the system T acts as a pair of coplanar lenses with opposite focal lengths and principal points offset in a transversal direction. To describe the imaging due to system T in lens imaging coordinates mathematically, we first find the intermediate image u prime v prime w prime due to D. By definition, this is of the standard imaging equation. Then we reimaged this intermediate image u prime v prime w prime by lens L3, whose principal point position is HU HV0 and focal length G3 is equal to -f. We obtain the final image u double prime v double prime w double prime, whose relation with the object position u vw can be described by this simple matrix equation. Then we transform this equation back to the Cartesian coordinates, and performing the matrix multiplication on the right-hand side finally yields this huge and horrible matrix equation. Fortunately, this equation simplifies significantly if the following assumptions are satisfied. First, angle theta is equal to minus theta prime, angle beta is equal to offset HV, which is equal to 0, and the ratio HU over F is equal to minus sine theta prime minus theta, where we denoted this angle delta theta. Applying this, the equation will get this form. And applying that the point P prime is the point P rotated around line V by angle delta theta, as can be seen in this figure here. This finally gives this nice simple equation, which states that the mapping between object space and image space is a pure rotation around line V by angle delta theta. Therefore, we will call the three-lens system T a skew-lens image rotator. The formulas for the parameters of the skew-lens image rotator are provided in the conference paper which comes along with this presentation. Provided physical realizations of tilt-lens image rotators can be made to work well enough, these devices might well find use in existing applications of optical image rotation. Some applications are discussed in the conference paper. Here, I want to discuss another potential application for the skew-lens image rotator. Recently, we proposed a novel approach to optical simulation of curved spaces. The strategy is based on the idea of unfolding manifolds into a flat space, so the light rays propagate as in a flat space inside these flattened manifolds. As for example here. When unfolding the curved space, wedges of missing space appear. To preserve the topology of the manifold even after such an unfolding and flattening, the faces of the wedges of missing space need to be equipped with gluing instructions, which ensure that these faces are identified with each other mathematically. In the corresponding optical simulation, the faces are identified optically by a device that transfers the optical field between the two faces of the missing space. Such a device is called a space-canceling wedge. Regarding just ray optical simulations of curved spaces, a skew-lens image rotator is an appropriate candidate for a space-canceling wedge. That this is indeed the case for a surface of a tetrahedron can be seen in this figure. Panel A shows an unfolded net of a surface of a regular tetrahedron surrounded by three ideal lens space-canceling wedges, each providing an image rotation by an angle delta theta equal to pi. Panels B and C present ray tracing simulations of the view of a white sphere located on the surface of a tetrahedron as seen from within the surface, with an added third Euclidean dimension perpendicular to the surface. Whereas B shows the simulation with skew-lens space-canceling wedges, C presents the same scene with perfect space-canceling wedges. In panel B, we can see white vertical lines, which are caused by the fact that light rays are missing the lenses completely, some of them, of course. This appears to be a fundamental defect, which cannot be removed completely, but significantly suppressed by tuning the parameters of the skew-lens image rotator. Okay, so just to summarize, we formulated a theory of imaging with systems of non-parallel lenses and applied it to design image rotating devices, which can be then employed, for example, in optical simulations of curved spaces. At the end, I would like to thank my collaborators, Dr. Johannes Kurtiel and Dr. Gergely Ferenczi, for a great time spent on this work, and you for your attention.